in this set of 3 lectures, I introduce you to certain elements of semi-classical gravity, which essentially corresponds to the study of the behavior of quantum fields in a gravitational background. The background is fixed and you are interested in studying some properties of quantum fields in this given background. And there are many interesting phenomena that occur in gravitational backgrounds, and importantly, there is some similarity to what happens in gravitational backgrounds and the study of quantum fields in classical electromagnetic backgrounds. So, some of the phenomena are the Casimir effect that occurs when you have plates, conducting plates kept in the vacuum, and what one finds is that there is a certain attraction between the plates even in the vacuum. And there is another phenomena that occurs in an electromagnetic background. If you have a sufficiently strong electric field, there can be pair production of pairs of, say, electrons and positrons even in the quantum vacuum. This is known as the Schwinger effect. Similar phenomena also occur in a gravitational background. The first example I gave you about the Casimir effect is referred to as vacuum polarization. Essentially, it is vacuum which is different from what you would have in the absence of the plates, which is the Minkowski vacuum. The second phenomena is referred to as particle production, and as I was mentioning, both these phenomena occur even in a gravitational background. One of the classic examples of vacuum polarization is something that is referred to as the Unruh effect, wherein a uniformly accelerated observer sees the Minkowski vacuum as a thermal bath of particles. There is an important dynamical phenomena which is closely related to this Unruh effect. As I will discuss, the Unruh effect is closely related to the fact that there is a horizon that the uniformly accelerated observer sees. As I was mentioning, a closely related phenomena to the Unruh effect is Hawking radiation, namely the production of a thermal spectrum of particles by a collapsing black hole. And this also leads to the idea of black hole thermodynamics. All these constitute essentially semi-classical gravity, which is what these lectures will focus on. This set of lectures will consist of 3 lectures, and in the lecture 1 I will talk about some essential classical field theory. I will talk about normal modes, okay, and how you normalize these modes and what do you mean by completeness of these modes, and these will be used when I talk about quantum field theory, quantization of a field in a given background. As you can imagine, I will first talk about quantization of a field in flat spacetime or Minkowski spacetime, and we will talk about polarizing the quantum vacuum. I mentioned the phenomena of vacuum polarization occurs when you have non-trivial boundaries such as Casimir plates. I will talk about that, and I will also discuss about the Unruh effect that I mentioned. That will be the content of the first lecture. In the second lecture, I will talk about something known as dynamical Casimir effect. I described to you what a Casimir effect is, but if you take a single plate, where the electromagnetic field, there are some boundary conditions have to be imposed on the electromagnetic fields, and you start shaking this plate. In the presence of a single plate or 2 plates, you will have something like the Casimir effect, but if you keep one plate and start shaking it, there is something called a dynamical Casimir effect, which essentially means it will throw out photons. Photons are produced by the action of moving this mirror. And then I will discuss about the Schwinger effect I mentioned, wherein if you keep very strong electric field even the vacuum, it starts producing pairs of particles in the vacuum. Essentially what you have is that you have a strong electric field. As I will describe later, you will have these virtual pairs of particles that can arise in quantum field theory, but they will come out, an electron positron pair will come out and annihilate themselves after a certain amount of time, as governed by the energy time uncertainty principle. But the moment you have an external field like the electric field or a strong gravitational field, which I will talk about later, what happens is that these pairs do not merge later, but they are just actually ripped apart from the quantum vacuum, and they end up as producing real particles. Okay? And that is what the Schwinger effect is, and in some sense that is what Hawking radiation is, as this famous picture goes. You know, there is a pairs of particles that emerge from the quantum vacuum, but one of them falls into the black hole and other goes away to infinity. I will talk about this later. And I will talk about particle production in a gravitational background. We will see when there is a time dependent gravitational field, such as collapsing black hole I talked about, a much simpler system to study. Black hole has horizons, etc., and the modes are more complex. A much simpler system where you can illustrate this phenomenon of particle production easily is when you have a time dependent gravitational field, as in an expanding universe, for instance. Okay? If you have a varying background, you know, time dependent background, and you study quantum fields in this background, what you will find is that there is a generation of particle antiparticle pairs, very much like what happens in the case of the electric field. Then I will talk about, in the third lecture, thermodynamics of black holes. I will describe how the laws of thermodynamics, black hole thermodynamics, were formulated. I will not have time to describe them in great detail. I will just outline those laws, and I will narrate this famous story as to how, you know, until 1973 or so, you know, there was this strange notion that black holes had entropy but had no temperature. And this is where Hawking's genius came in, where he showed that black holes actually evaporate. They are not completely black as in classical physics, but the moment you study the evolution of a quantum field in an evolving black hole, you will find that there are particles produced by this collapsing black hole, and they are seen at, you know, far away as a thermal spectrum of particles. And this was a crucial input that had to be provided in order for the black hole laws of black hole thermodynamics to be consistent. And I will, of course, in this process describe Hawking radiation itself, and then I will talk about imprints of Planck scale physics. There are two places where this has been studied in some detail and some understanding has been gained. These two places are where, you know, are inflation and black hole physics. Inflation is something that may be more familiar to you, where you have modes are stretched exponentially during this 60 odd e-folds of inflation. Or if you go back, you take a scale, cosmological scale of about a megaparsec or so, and allow for 60 e-folds of inflation, track it back through a matter and a radiation dominated epoch to the early stages of inflation. When you impose these famous Bunch-Davies initial conditions, you will find that the wavelength of this mode corresponding to 1 megaparsec today would have been of the order of Planck length. So the concern was raised as to whether Planck scale physics will modify the primordial spectrum. I will talk about our current understanding of this so-called trans-Planckian problem, and what one finds is that there is such an exponential redshifting even in the case of black holes. So what happens is that you impose the initial condition, as I will describe later, at very early times, you know, which is referred to as the Unruh vacuum. I will describe this in the third lecture, and you have to evolve these modes, you know, and what happens is that they will, as the black hole collapses into the Schwarzschild radius, what you will find is there is an exponential redshifting of these modes. And in the same fashion as you do in the context of cosmology, you take a mode at Scri plus in future null infinity and ask what is the wavelength of the mode at Scri minus at past null infinity. When you impose the initial conditions on the quantum field, you will find that the modes are trans-Planckian. This is discussed in standard texts like standard texts like the Wall's text on general relativity. And the concern is whether, you know, Planck scale physics will modify Hawking radiation, and there was even concern whether it will wipe out Hawking radiation. I will briefly discuss these effects in the third lecture and summarize. So a few words on my conventions and notations. We shall work in units such that C and H bar are 1, and also we shall adopt the convention wherein the signature of the metric is such that time-like separated events are described by positive space-time intervals, which essentially means that in 1 plus 1 dimensions, if you are working in Minkowski space-time and you are describing the Minkowski space-time in terms of the standard inertial coordinates, then the line element is given by this expression. It is dt squared minus dx squared. So, I have plus minus signature. To illustrate many of my points, I will largely work in 1 plus 1 dimensions. In some cases, I will extend some of these arguments to 3 plus 1 dimensions when it does not make a significant difference to whether I am studying in 1 plus 1 or 3 plus 1 dimensions. And the convention is that Greek indices shall denote space-time coordinates, while the Latin indices shall denote the spatial coordinates. And importantly, you will constantly encounter this x tilde. It is a convenient shorthand for me to denote x mu. And to highlight the essential physics in terms of simple terms, I will often consider, actually always consider the quantum field to be a massless scalar field. And this is just for simplicity. All these arguments can be extended to other fields as well. What the background you require? I expect you to be familiar with some elements of classical field theory, like the action principle, and we will need the equation of motion for a scalar field, because that is what I am going to focus on. And as we will see later, the quantum field theory requires the classical modes. It is using these classical modes you quantize your field, and you will need to know the idea of a stress energy tensor. The quantum mechanics, for all purposes, what I need is quantization of the harmonic oscillator, which I presume all of you are familiar with. What I will soon describe is how any field, free field, can be decomposed in terms of a collection of oscillators, a collection of modes, okay? And if you quantize, when you say you quantize the field, you are essentially quantizing each of these oscillators. And you will need to know the generalized uncertainty principle. I just need it for one simple argument, and then I am hoping that you would have had some exposure to general relativity. I presume you would have heard about non-inertial coordinates in flat space-time. A simpler non-inertial coordinate is the rotating frame that is easy to consider. A more non-trivial non-inertial coordinate system, which we will be interested in, is this uniformly accelerated observer. I will write down the specific transformations in due course of time. Of course, we will talk about black holes. I expect you to know at least the Schwarzschild metric, and I assume you know about the Friedmann line element. So, as I mentioned, there will be 3 lectures. The first lecture will consist of the following. I will quickly go through some essential aspects of classical field theory, which we will use to quantize the field, and then I will talk about quantizing the field in flat space-time, and then I will talk about these 2 phenomena which are essentially due to vacuum polarization, namely the Casimir and the Unruh effects. So, we start with some simple classical field. For simplicity, as I mentioned, we will work in 1 plus 1 dimension, and here is the action. S is the action. Remember, x tilde implies all the space-time coordinates, x mu, and L, script L, is the Lagrangian density, which I have written explicitly on the right side. And d mu phi is essentially d mu d phi by dx mu. It is the partial derivative with respect to x mu. G mu is the metric tensor describing the space-time, and G is the determinant of the covariant metric tensor G mu nu. And as you know, if you vary this action, I should emphasize we will soon discuss the case of flat space-time. In this slide, it applies to an arbitrary curved space-time. You will be familiar with the fact that in flat space-time you will have the equation of motion to be the D'Alembertian times phi equal to 0, and in flat space-time the D'Alembertian has a simple structure. It is just d mu, and all that happens is that the ordinary partial derivative gets replaced by the covariant derivative, and therefore you have grad mu phi equal to 0. And what I would urge you to do, if you haven't done that earlier, show that it can be written in this particular form, where you have 1 over root minus g d mu root minus g mu nu d mu phi equal to 0. As I have emphasized already, the solutions to this classical equation. So you give me a classical background, okay. For instance, you give me a metric tensor describing the Minkowski metric in the frame of a uniformly accelerated observer, or it could be the Friedmann line element, or it could be the space-time of a black hole. Before I quantize, what I need are classical solutions. So I need to solve this wave equation at least approximately in this given background. And evidently we are going to start with the simplest background possible, namely Minkowski spacetime. One of the important things you need to appreciate about a field, something I have mentioned already, is that it can be decomposed into a set of modes which, in the simplest of situations, like the case of a Minkowski spacetime, reduces to a collection of oscillators. In the Minkowski spacetime, there is no time dependence, there is no background time dependence, there is no space dependence, and therefore I can simply Fourier transform this field using this relation. And phi, the scalar field that I am considering, is a real scalar field, and therefore phi equal to phi star, which implies that qk is q minus k star. There is a relation between the minus k mode and the plus k mode. And now what you can do is that you can take this Fourier decomposition and plug it in the original action that we had, namely this guy, okay, working in the case of flat spacetime, which means g mu nu is eta mu mu, and ask what happens. Well, what you obtain is the following action. So you have a collection of oscillators, in fact an infinite collection of oscillators with mass unity and a frequency which is given by k, or rather omega, which is modulus of k. The frequency is positive. Now I can vary this action of describing this collection of oscillators, and evidently you will obtain this equation which governs an oscillator with a frequency k. I should have written omega squared, with omega being mod k. Notice k goes from minus infinity to plus infinity. And evidently I can have solutions of the form e power plus or minus I omega t. Now what do you do in a general background? It depends on the symmetries that the background permits. You can always decompose the modes of the field in a suitable set, and what you need to do is that you will have a collection of normal modes, many of which will behave as oscillators. For instance, if you have a time dependent background, you will actually have a collection of time dependent oscillators, and it is this time dependence which causes interesting physics like particle production. Then why does the vacuum polarization arise? It arises because the form of the modes may remain same, but they are slightly different because of boundary conditions between the parallel plates. So the distribution of the modes are different, and therefore it leads to phenomena like the Casimir effect. The bottom line is that given a background, you decompose in terms of the normal modes, and the normal modes, as you will appreciate as we go along, play an important role, and it is the structure of the normal modes that determines the quantization and the corresponding physical effects. So what are the normal modes in flat space time? What we are doing is that we are going back to the original equation, box phi equal to 0, and solving for these modes, and in 1 plus 1 space time dimensions, they are of this form. And this is a structure e power minus I omega t minus kx is something you will be familiar with. It describes a travelling wave, and these constants that appear in front of these normal modes, it will become clear as to why we need these constants later. They are not so important in classical field theory, they are important in quantum field theory. And Another thing I have chosen is that I have written it as e power minus I omega t minus kx. This also will play an important role later, and you may ask, why didn't I choose e power plus I omega t instead of e power minus I omega t? Again, this will become important when we quantize the field. Of course, this 1 plus 1 dimensional solution can be easily extended to 3 dimensions, where when you write in this Lorentz invariant notation, it is still e power I k mu x mu, and you write it explicitly in terms of the coordinates, you have omega t minus k dot x, and omega is evidently modulus of k. As I mentioned, I will later describe the appearance of these factors like 2 pi and 2 omega, and the choice of e power minus I omega t in contrast to e power plus I omega t. Now, I have a collection of modes. In principle, any given classical field phi of x can be decomposed in terms of these normal modes. Remember, phi is a real scalar field. So I have to write something c k u k plus its complex conjugate, which is c k star u k star. And c k in classical physics are determined by the initial conditions that are given to you. For instance, if you are told that a classical field consists of only one mode, k equal to k naught of a certain amplitude, then you will have c k to be something like a Dirac delta function associated with the mode, and a is the script a is the amplitude of that mode. So, what happens to normal modes in a general background? They are again obtained by solving the equation of motion of the scalar field in the given background. I should clarify that if you have boundaries present, right, if I have free space, you will have just e power minus I omega t minus k dot x, but the moment I have boundaries present, for instance, remember your quantum mechanics, free particle, the wave function, the spatial part of the wave function is just e power I k x plus or minus I k x in one dimension. The moment I confine it to a box, it becomes sin kx, and importantly k, which was originally continuous in the case of a free particle, becomes discrete because of the presence of these boundaries. Something similar happens when you have these Casimir plates, as we will see, and that makes a considerable difference to the physics. Evidently, the symmetries of the background will determine the form of the normal modes. I wrote this down. I wrote this wave function down in 3 plus 1 dimension, 3 plus 1 space time dimension. This is assuming we are working in Cartesian coordinates. The Minkowski metric has all the symmetries. I do not need to work in Cartesian coordinates. If you have not done this already, one of the exercises you should do is understand what are the normal modes of a massless free scalar field when you work in cylindrical polar coordinates or spherical polar coordinates. And you can imagine what will happen. Firstly, time translational invariance implies that the modes can be decomposed as e power minus I omega t. Again, you will ask, why not e power plus I omega t? That answer lies when we talk about quantum field theory. And translational invariance along a specific direction, say x, implies I can write the normal modes at e power I k x x. In 3 plus 1 dimensions, there can be azimuthal symmetry. You may want to study quantum field around a cosmic string spacetime. This is one of the exactly solvable situations. And there is an azimuthal symmetry that is available to you. So, the modes will be of the form e power I m phi. Or you may have spherical symmetry like the spacetime of a black hole, or the much simpler Minkowski spacetime. What I would urge you to do is construct the solutions to the wave equation in terms of these cylindrical and spherical polar coordinates. You will appreciate what is the relation between the symmetries and the normal modes. Now, we should talk about the normalization of the modes, and this can be carried out using a conserved current, very similar to what you do in quantum mechanics. The normalization of the wave function is achieved with the help of a conserved current. And you can immediately show, you can define a conserved current which is given by this expression J mu, which is phi del with this double edged arrow, okay, which is given by this expression. So, it is phi del mu phi star minus phi star del mu phi. It is immediately evident that the current is conserved, because all you need to do is operate del mu on j mu, okay, and what you will have is that you will have terms like del mu phi star, which will cancel, and there will be terms like del mu phi and del mu phi star, both of which are 0, because phi and phi star satisfy the wave equation. So, you have a conserved current. Using this conserved current, you can define a normal product, a scalar product between two modes UK and UK prime. I should emphasize the top part of the slides, or in fact all the parts of the slides, does not confine to only flat space time. In the earlier slides we had talked about flat space time. These arguments are general and apply to any generic curved space time. Utilizing this conserved current, we can define the scalar products between modes UK and UK prime to be given by this expression. So, let me clarify a few things. I have already defined what is this UK del mu with this double arrow UK prime star. This d sigma mu can be written in this fashion: d sigma times n hat mu. N hat mu is a future directed unit vector which is orthogonal to a space like surface, okay, and the space like surface is defined by sigma, and d sigma is a volume element on sigma. And you will appreciate it if I give a simple example. For instance, you can, in flat space time, if you are working in, you can choose this to be a constant time surface, n mu will be perpendicular to that, all right, and d sigma is the volume on this constant time surface. It is an infinite volume on this constant time surface. So, for instance, it is dx, dy, dz in 3 plus 1 dimensions, or just dx in 1 plus 1 dimension. So, now what you can show is the following. Remember, I had introduced you to UK earlier in 1 plus 1 dimensions. These are the ones, and what you can show is that if you use this scalar product on a constant time surface, you can show that UK prime is given by this Dirac delta function plus Dirac delta function, and UK prime star is minus times the Dirac delta function of k and k prime. I would urge you to show that. In other words, UK have positive norm and UK star have negative norms. Now, there are two things I need. One, I need scalar product. When I try to decompose a field in terms of its modes, I need to define scalar products so that I have orthonormal modes, and then I need to show that the modes are complete. How do you define the completeness of the modes? And they are defined as follows. So, for instance, in the simple case of 1 plus 1 dimension Minkowski space time, the completeness relation is given by this expression. You can generalize it to an arbitrary space time, okay. It is a little tricky to do so. It is easy to illustrate it in the case of Minkowski space time. So, what you have is that, remember, the k is the one that describes the normal modes, and k goes from minus infinity to plus infinity in 1 plus 1 Minkowski, and you just have to sum over the modes, okay, in a suitable fashion, and this is essentially, notice it is just grad mu, with the double vector on a constant time surface. That is all there is to it here. And this reason behind this choice of normalization will become clear. This choice of demanding completeness in this way will become clear when we talk about quantization of the field. And it should be evident that if you extend this argument to 3 plus 1 space time dimensions, it will be of this form. So, we have everything we require to discuss quantization of a field. And now I will introduce you to the canonical quantization procedure. I will talk about it in flat space-time. It is relatively straightforward to extend it to an arbitrary curved space-time. All you need are normal modes and a corresponding completeness relation. And then I will introduce you to the idea of vacuum in quantum field theory. Earlier, we had decomposed the classical field phi in terms of the CK UK plus its complex conjugate. When you say you quantize a field, what you do is that you elevate these classical quantities Ck and Ck star to quantum operators. Phi is real, therefore, the corresponding quantized operator should be Hermitian, okay? And therefore, what you do is that you replace Ck by Ak hat and Ck star by Ak dagger. So, the second term is Hermitian conjugate of the first term. And where we will see is that where we will soon show that Ak and Ak dagger correspond to the annihilation and creation operators associated with each mode of the quantum field. I have been harping on the fact that a field is nothing but a collection of oscillators, and we know each oscillators come with an A and A dagger. Now, these different oscillators correspond to different K. So, if I quantize my oscillators, I have essentially quantized the field. What you do is that you impose canonical quantum commutation relations, and we will see these canonical commutation relations will lead to the commutation relations for these A and A dagger that you should be familiar with. So, we need to construct the canonically conjugate momentum associated with the field, and you can show in a generic curved space time it is given by this expression. It is the time derivative of it is the derivative of the Lagrangian density with respect to the derivative of the time derivative of the field, and you can show from the Lagrangian density that we had earlier, it is given by this expression. And if you are working in Minkowski space time, it has a very simple form. It is essentially phi dot, where phi dot is d phi by dt. I am sorry, this should have been partial dou phi by dou t. It is just the time derivative of phi. So, given this guy, the phi hat, I can construct the corresponding pi hat. I know the modes in a given background, and I can construct the corresponding pi. In particular, in Minkowski space time, it is trivial, it is just d phi by dt, which means all that will happen, you know the form of the modes. This will have a e power minus I omega t, and this will have e power plus I omega t. They will pick up a minus I omega here and a plus I omega here, nothing more. Now, I impose the standard canonical quantization relation. This is like x and p associated with each oscillator. So, what do you have? You have phi phi commute, okay, on at the same time, pi and pi commute, but phi and pi have this relation, which is a Dirac delta function. Now, as an exercise, what you should do is that I have already explained to you what are UK, that I had them earlier, okay, and we have already discussed what is phi dot, which is pi. So, you can construct pi hat. So, if you demand this commutators, these three commutators, you will find that they correspond to the corresponding they correspond to the following commutators between AK and AK dagger. And evidently, in 3+1 dimensions, the above commutation relations will be given by this form. All that happens is that there is a k vector now, and instead of spatial x just one dimension, they correspond to 3 dimensions now. It is straightforward to extend this quantization to 3 dimensions. This is where the choice of the e power minus I omega t as the coefficient of Ck in the original classical decomposition, and the corresponding quantum decomposition will become clear. Before I discuss this, I should make a couple of remarks. The completeness relation that I had talked about here, this one and this one, are required to ensure that we have this result here and this result here. Okay? If you do not have those completeness relations, all right, you will not obtain these canonical commutation relations that you have demanded. Okay? So, I have talked about normalization of the mode already, that could be understood completely from the conservation of the current associated with my wave equation, and I have now illustrated why demanding completeness of the modes have that peculiar structure. It is to ensure that phi and pi satisfy the commutation relation as described here. Now, I need to explain why we have written the UKs with a e power minus I omega t. Notice in this decomposition, AK is the coefficient of UK. UKs have positive norms. Remember, UK prime was a plus Dirac delta function, while UK star, UK prime star was minus a Dirac delta function. Okay? So, they have positive norms, and these guys are referred to as also positive frequency. The e power minus I omega t with omega greater than 0 also have positive frequency. In Minkowski space time, in the inertial coordinates that we are working in, there is no such distinction. Positive norms correspond to positive frequency and vice versa, but they can be different if you work even in non-inertial coordinates in Minkowski space time or in other non-trivial space times. And remember, it is the coefficient of the positive norm mode that is identified to be the annihilation operator AK, and the vacuum state is defined with respect to that particular annihilation operator. The vacuum state is defined as AK operating on this vacuum state is 0 for all modes k. This is the definition of the vacuum state, and this applies not only to flat space time, it also applies to curved space time. The point is that in a curved space time like a Friedmann universe, as we will see, the solutions may not reduce to the form e power minus I omega t nicely. What you will call as positive frequency modes at early times may not remain positive frequency modes at later times, and this, as we shall see, leads to the idea of pack creation, and that is closely related to the definition of the vacuum in the way we have done here. And an important aspect of quantum mechanics is the uncertainty principle. In classical mechanics, position and velocity can be specified simultaneously, but not so in quantum mechanics. In quantum mechanics, conjugate variables satisfy the uncertainty principle. For instance, x and p do not commute, and therefore, you can have delta x delta p to be greater than, you need to have delta x delta p, where delta x and delta p are the uncertainties in x and p to be greater than half. Remember, we are working in units wherein h bar equal to 1, that is why you have half rather than h bar by 2. And you should be familiar from your quantum mechanics that these arguments can be translated to uncertainties in energy and time of a particle to be delta E, delta T to be greater than half. Why am I discussing this? This will become clear in the next slide. The vacuum in quantum field theory is not truly a vacuum, it is a beehive of activity. And as we have been discussing, quantum field theory essentially involves extensions of principles of quantum mechanics to fields. As I have been emphasizing, you decompose your field into oscillator and quantize each mode of the oscillator, and you have quantum field theory. And the vacuum is not devoid of activity, but it is buzzing with activity. Because of the energy time uncertainty principle, I can have two pairs of particles which can emerge out of the vacuum. Here there are electron positron pairs which arise and they can annihilate provided delta T is less than delta E, which is essentially 2 times the mass of the electron in this case. And therefore, there are always these vacuum fluctuations that are present. And how does this reflect in quantum field theory? We will see it reflects in the behavior of the propagators in quantum field theory. You can have in quantum mechanics, this is time. So, the propagator will be 0 if you consider on a constant time. The propagator will be non-zero as you go from t to t prime with t prime greater than t. If you are familiar with the Feynman propagator in quantum mechanics, there is always a theta of t prime minus t. T prime has to be greater than t. Otherwise, the propagator is 0. But not so in quantum field theory. We will see the propagator, or equivalently the Green's function, we will encounter a particular type of Green's function called the Whiteman function, can be non-zero even on a space-like surface. It will become evident when we calculate some of these quantities, and that is essentially a reflection of the presence of these virtual particles. And this is the Whiteman function I talked about. An important quantity characterizing the quantum field is the 2-point correlation function, and the 2-point function we will be interested in is something called the Whiteman function. It is given by this expression, and this is the Whiteman function. I don't need to write O subscript m, it corresponds to the Minkowski vacuum, but this is a definition I can define in any space time, okay, or any background with a phi decomposed in terms of the corresponding modes and a vacuum chosen suitably. We have already decomposed the field in 1 + 1 dimensions in Minkowski vacuum, and using the normal modes you can immediately construct. Remember, we had decomposed the field in this fashion, right, in this fashion, and the vacuum state is the state that is annihilated by the AK operator, the annihilation operator, and we know UK as well. These are the normal modes that we have discussed about. So, it is straightforward to construct this 2-point function, this Whiteman function. Just a few words on the notation. D is the Whiteman function often for a massless field. D is the notation that is used for a massless field. This D plus is phi x prime, and D minus is phi x prime phi x, and the remaining Green's function can be constructed in terms of D plus and D minus. So, using the modes that I had introduced earlier, you can immediately show that D plus x prime can be written in this form. And all I have done in the second line is divide this into, because there is a mod k, I have divided into minus infinity to 0 of k and 0 to infinity in k, and then I have changed variables from k to minus k. There is something more that I have introduced. Look at the original expression on top here, all right, or even look at any of these, either the first line or the second line. Consider the case where t is t prime, okay. Actually, look at the first one, ignore the second one because it contains an epsilon. Look at the first one. When t equal to t prime and x is equal to x prime, you are left with an integral which is dk by k, which is essentially logarithm. And now, if you impose the limits, the logarithm diverges. You will encounter divergence in quantum field theory, and the coincidence limits of these propagators will diverge, and you need to ensure that the integrals converge, and this is why you have introduced this infinitesimal parameter called epsilon. It is a small positive quantity. This is introduced to ensure convergence of these integrals. The logarithmic divergence that we are encountering here is a peculiarity of 1 + 1 dimension. Remember, if you have a logarithm, it can diverge at, logarithm of x will diverge at large x as well as small x, x goes to 0 as well as x goes to infinity. That is a peculiar property of massless fields in 1+1 dimensions. If you do the Weightman function in 3+1 dimensions, which we will discuss later, it will not diverge in the infrared limit, it will diverge only at the ultraviolet limit, or large k or small x alone. So, now having introduced this cutoff through this epsilon, you have truncated the integral in a suitable manner, or regulated the integral, not quite truncated, and you can integrate this to arrive at this d plus in this form. It is a logarithm essentially of sigma squared, where sigma squared is the Lorentz invariant space time interval, and mu has been introduced, so that it is a logarithm of some quantity, okay, and the mu has been introduced to ensure that the coefficient or the argument of the logarithm, sorry, is dimensionless. Now, what happens in 3+1 dimensions? As I mentioned, you can use the modes that we had earlier, and you can reduce it to the form that is written here, and you can carry out the integrals again. The angular integrals are straightforward to do, and I hope you would have calculated something like the retarded propagator in classical field theory, if you have done your course in classical field theory. So, the angular integrals are easy to do. You need a regulator to calculate the radial integral, or the integral along k, and that you introduce a regulator through an I epsilon, just as you had done in the 1+1 dimensional case, and you can arrive at this Weightman function, which is 1 over sigma squared essentially, where sigma squared is now the Lorentz invariant interval in 3+1 dimensions. We will make use of this when we discuss about the Unruh effect later. Another useful quantity which we will need is the stress energy tensor associated with the scalar field. I presume you all know how to construct the stress energy tensor, you would have been exposed to it in general relativity. You vary the action with respect to the metric tensor, and then if you use this relation, you can construct the corresponding stress energy tensor. You are varying the action with respect to the metric tensor because in general relativity, all right, the varying the action corresponding to gravity plus matter leads to the Einstein's equations, and the stress energy tensor is the source of the Einstein equation, and therefore, when you vary your matter action governing your matter field, here it is a scalar field, with respect to the metric tensor, you will arrive at the stress energy tensor. For the specific form of the action that we had earlier, you can immediately construct the stress energy tensor to be of this form. And in 1+1 dimensions, if you are working in inertial coordinates in Minkowski spacetime, they have a very simple structure. Often we will, there are some cases where we will talk about other components as well. One of the things we will focus on is the TT component, which is the energy density of the scalar field. Now, let us calculate the expectation value of the energy density. As I just mentioned, rho is just T upper T and lower T of the scalar field. Let us calculate it in the Minkowski vacuum. You can take the modes that you had earlier. Notice the stress energy tensor consists of derivatives of, or rather products of the derivatives of the field. The Green's function that we had earlier had consisted of products of the field, and you know that they will diverge when you take the coincidence limit. So, it is not surprising that when you calculate this expectation value of the stress energy tensor, they will diverge. Okay? So, what you should do is that you should take the quantized field that we had earlier, use this expression for the stress energy tensor, particularly the energy density, all right, and you calculate what is the expectation value in the Minkowski vacuum in a manner very similar to what you had to do, what you had done for the case of the Weightman function, okay, but it is just that here it involves derivatives of the fields. And what you can show is the following. This is again not surprising at all, right. We have been saying, for instance, if you are working in Minkowski vacuum, I am sorry, in Minkowski space-time, and you are working inertial coordinates, and you know they are all collection of oscillators. And what do you have? Each oscillator has an energy omega by 2. Remember, h bar is 1, and therefore, the energy density of the field will be sum over the energy densities, I am sorry, the sum of the energies of the ground states of these oscillators. But you have infinite collection of oscillators, therefore, the energy density evaluated in the Minkowski vacuum, it is just dk minus infinity to plus infinity. Remember, k goes from minus infinity to infinity, omega by 2, where omega is mod k. And not surprisingly, the energy density diverges. In fact, it will diverge faster than the Weightman function itself. I presume it is clear. Remember, the Weightman function had diverged like dk by k. The energy density diverges dk times k. Okay, it will diverge faster, and in 3 plus 1 dimensions you can immediately show that it has the same form. It is a sum over all the oscillators. There are more oscillators now along 3 directions, okay, times omega by 2. Now, how do you calculate this energy density? Well, I have to somehow regulate the integral just as I had done to calculate the Weightman function. I can introduce a regulator here, all right, in a manner similar to that I had in the context of calculating the Weightman function. And if you can calculate this integral, this is not difficult to do. One finds that it diverges as 1 over epsilon square. Okay. It is not surprising. Notice this diverges as k squared. Epsilon has dimension of 1 over length, right. Therefore, it diverges as 1 over length squared, which is like k squared. Now, we need to move on to understand what the Casimir effect is all about. It is very easy to understand. What happens is that the moment you introduce some boundaries in your space-time, here space, the modes change. The free particle versus particle in a box. In both the cases, you have an infinite collection of oscillators. Remember, the free particle modes go from n equal to 0 to infinity, I am sorry, k equal to minus infinity to plus infinity. In the case of a particle in a box, the mode go from n equal to 0 to infinity. It is always infinite. But what you will see is that the difference between these infinities will be finite, and this is actually an observable quantity, which is essentially the Casimir effect. So, I am not going to impose boundary conditions on 2 plates, which will correspond to the actual Casimir plates, which I mentioned has been experimentally observed. We will, for simplicity, for mathematical simplicity, I am going to assume a periodic condition on my quantum field. So, in other words, I live in a closed universe. Okay. So, but my universe is just one dimension. So, my universe is just a circle. But because of the fact, in the case of a particle in a box, the wave function has to vanish here and the wave function has to vanish here. But you would have done particle on a circle, for instance, it has to satisfy periodic boundary conditions. So, the modes are also simpler. They are not sine, they are just exponential. It is just that there is periodic boundary condition, and therefore, what do you have? My k is not continuous, okay, because e power I k x should be the same as e power I k x plus L. Okay. Therefore, k is discrete and they are given by 2n pi by L, n being an integer. An integer can go from minus infinity to plus infinity. Now, I can decompose my modes of the scalar field. So, what do we have? I just have a quantum field on the circle essentially. I can decompose my modes exactly as I had done in the case of the Minkowski modes, but it is just that the modes are discrete, and therefore, there I have a different set of AK and AK dagger. I should have probably written it as AN and AN dagger to be precise. and I have a new vacuum. Because my modes are different, and remember the coefficient of the positive norm or positive frequency modes is supposed to be the annihilation operator, and it is this annihilation operator which allows me to define my vacuum state. And so I have a different vacuum 0 sub c, which is referred to as the Casimir vacuum. So what I can do is that I can go and calculate the energy density associated with the vacuum in the same manner I had calculated the energy density in the Minkowski vacuum. I should emphasize a couple of points. Notice here I have constructed a set of normal modes and it contains L because of the periodicity is L. Okay? So you need to show that the normalization leads to this L. I will leave it as an exercise for you to work it out. So what do? We calculate the energy density. You can plug in all that expression, and I should emphasize this expectation value is evaluated in the Casimir vacuum 0 sub c, and it is not surprising that you will have sum over the modes with omega by 2, omega is mod k here. You had an integral earlier in the case of the Minkowski vacuum, now you have sum because you have a discrete set of modes. And again you have a divergent quantity, okay. The sum can be easily written like this, sum over n equal to 0 to infinity, it is evident it is going to be divergent. And if you are familiar with zeta functions, it is zeta of -1, all right. And the problem is you have to truncate this somehow, you have to regulate this sum now. So what I do is as follows, I introduce a regulator which is just essentially e power minus epsilon k that I had in the case of the integral, but just that k is 2 n pi by L, and therefore I have a regulator like this. Now what I can do, what you need to do is as follows, you can calculate this sum exactly. Remember, epsilon is supposed to be a small quantity. Once you calculate the sum exactly, I would urge you to Taylor expand and retime, this alpha should have been epsilon, I am sorry about that typo, okay, and you should expand at small epsilon. So you will have something which is divergent as epsilon goes to 0, not surprising because your original sum is divergent as epsilon goes to 0, and then you will have a finite term, and then you will have additional terms which vanish as epsilon goes to 0. Now what you find is that this, as I mentioned, it has to be 1 over 2 pi epsilon squared, but notice this is exactly the same 1 over 2 pi epsilon squared that we had in the Minkowski vacuum. The divergence is of the same form. So if I talk about difference in energy between the Casimir and the Minkowski vacuum, I am left with an expression which is minus pi by 6 L squared, which is actually the Casimir energy density in 1 plus 1 dimension. You can extend these arguments for the case of 3 plus 1 dimensions with more realistic boundary conditions rather than a periodic boundary condition. So as I was mentioning, the difference between rho sub c and rho sub m is finite. It depends on the size of your universe, so to say, or the distance between the two plates in a more realistic situation, and this energy is referred to as the Casimir energy. If I differentiate with respect to the distance, it gives me a force, and that is the Casimir force. And this is what I have said, the energy happens to be minus pi by 6 L squared for this specific situation I have described, and it is an observable effect. All these arguments that I have described here, the modes, the quantization, etc., can be extended to the case of the more realistic electromagnetic fields. There are some additional things you need to take into account. Remember, electromagnetic fields have polarization and they are transverse in polarization, etc. So you need to account for all of them, but those are just details. The quantization procedure runs very similarly, and you can evaluate this Casimir energy for a more realistic situation that you want to create in a lab, where you have real two large plates, conducting plates, just left in empty space. And you can carry out this exercise, and the force per unit area happens to be something like this. Okay. It evidently contains, I have reinstated h bar and c for you to calculate the numbers, and they are given by this expression. Okay. All right. And as I mentioned, it has been actually measured in the laboratory, and interestingly, the Casimir force, whether it is attractive or repulsive, depends on the shape of the plates. If you are considering a spherical conducting plates or more complicated geometry, it can be non-trivial, and there are a variety of geometry for which this Casimir effect has been calculated. And this is a phenomena of vacuum polarization. So, what has happened is that something non-trivial that you have imposed, boundary conditions, has changed the structure of the vacuum, and that has observational consequences. Remember, the second thing, as I said, that I will discuss in this lecture is this Unruh effect, which is again a vacuum polarization effect. The modes I had described earlier in the Minkowski vacuum describing a scalar field had an explicitly Lorentz invariant form. Remember, I had said they can be written as k mu x mu, and the vacuum state and other things that you have defined will be invariant under Lorentz transformation. It does not matter which inertial frame in which you carry out this quantization. A question of interest is whether this applies to nonlinear coordinate transformations as well. Why should I restrict myself to linear coordinate transformations? What happens if I choose to quantize my field in a non-inertial frame of reference? What I want you to appreciate is the following. Remember, I talked about quantizing the field in cylindrical polar or spherical polar coordinates. They are also non-linear coordinate transformation with respect to the original Cartesian coordinates. I am not talking about non-linear coordinate transformations of the space alone. That does not affect the Lorentz invariant property. I am talking about non-linear coordinate transformations of space and the time coordinates. If you go to a rotating frame, or as I shall discuss, a case of a not linearly accelerated observer, whether the quantization and the results that you talk about, results of quantum field theory will be invariant under these coordinate transformations. Now, what you will have is the following. When you carry out the quantization in two frames of reference, two different frames of reference, in simple cases it is just relabeling like the inertial transformations. But think of a nonlinear coordinate transformation that I am talking about. What will happen is that the metric changes, it has a different structure. So, the modes can be different as well. You are already familiar with it when you carry out such a spatial coordinate transformation. The modes change. But now you are talking about space-time coordinate transformations, nonlinear space-time coordinate transformations. So, the modes will be completely different. So, you have one guy who is the Minkowski or the inertial observer. Okay. Remember, we are in Minkowski space-time, but we choose to carry out the quantization in the frames of two different observers. We have already discussed the quantization in the Minkowski coordinates. For the sake of convenience, I have written a sum rather than integral. Let ui be the Minkowski coordinates that I have discussed already. I am sorry, the Minkowski modes that I have discussed already. These are the modes describing a scalar field in an inertial frame of reference. Let there be another coordinate system which is related to the Minkowski coordinates through a nonlinear coordinate transformation of space and time coordinates. I can solve the equation of motion of the scalar field in that frame of reference. They may not have the same simple form that you had in the Minkowski coordinate. They can be more complex depending on the choice of your nonlinear coordinate transformation. Let those modes be Vj. and I can construct normalization in that coordinate system as well. I just have to follow the same procedure that I had discussed earlier, and then I can decompose the scalar field. Apart from decomposing in this fashion in the Minkowski coordinates, I can decompose using a new set of creation and annihilation operators B and B dagger in this nonlinear coordinate system. And what one can show is that when you have two such complete set of modes, you can relate one set of modes to the other through something known as the Bogoliubov transformations, and they are given by this expression. So, let me emphasize again, you have two complete set of modes, one in the Minkowski coordinates and another in another coordinate system that are related to the Minkowski coordinates by a nonlinear coordinate transformation, nonlinear transformation of space and time coordinates. And the modes in that coordinate system, normalized modes, are Vj, and you can construct a complete set of modes in that frame as well. What it means is that I can carry out the canonical quantization procedure in the Minkowski coordinates and the new coordinate system. When I do so, I can relate one set of modes, say the Minkowski modes, through this relation, which are referred to as the Bogoliubov transformation. The coefficients alpha and beta are the Bogoliubov coefficients, are referred to as the Bogoliubov coefficients. Remember, Vj are the modes in the new coordinate system, Ui are my original Minkowski modes, and this sum is just a formal sum. It could be an integral, that could be a continuous set of modes. I am not suggesting it is discrete. And once I have this, I have already said both Ui and Vj are normalized set of modes. Using the orthonormality relations of Vj's, for instance, you can and this relation between Ui and Vj, you can immediately show that alpha ij is given by this scalar product on the left and beta ij is given by this product on the left. Now, let us go back to this expression. So, I can write Ui in terms of Vj and Vj star, and evidently I can do so with Ui star as well. So, what will I have? I will have a relation which will consist of A and A dagger and Vj and Vj star. I can combine them in a suitable fashion and compare with the second expression. It is the same scalar field which has been decomposed in terms of one set of modes or the other set of modes, and by comparing them I can relate the AA dagger to BB dagger. I hope the point is clear, and when you do so, you arrive at this relation for Bj. Once I have Bj, I can construct Bj dagger. It is just the Hermitian conjugate. Notice it contains a linear combination of A as well as A dagger if beta is non-zero. If the Bogoliubov coefficient beta is non-zero, B not only contains A, but A dagger as well. So, now I can define two vacua, one which is annihilated by B and another which is annihilated by A. The one annihilated by A is my Minkowski vacua. That is what we have been discussing all the while. So, if I try to calculate B dagger B, what does it imply? It is in some sense the number of particles associated with B, the new coordinate system, in the Minkowski vacuum. This expectation value has been evaluated in the Minkowski vacuum. It is clear, right? So, what will happen? A will annihilate the Minkowski vacuum, but A dagger will not. And therefore, when I calculate B dagger B, there will be a term like AA dagger which will ensure it is non-zero, and that will involve beta. So, if the Bogoliubov coefficient between these modes is beta is non-zero, what it means is that B dagger B will be non-zero. The Minkowski vacuum will seem like populated if you carry out the quantization with respect to this non-inertial observer, okay, even in the Minkowski vacuum. And this is what happens in the frame of a uniformly accelerated observer. And these transformations that carry you from the inertial coordinates to the coordinates of a uniformly accelerated observer are known as the Rindler transformation, and they are given by this expression. And I have written in a particular form so that the Minkowski metric takes this form. And notice this is conformal to the original Minkowski metric with a conformal factor of e power 2 g psi. Something one can show is that if there are two metrics that are conformally related in 1 plus 1 space time dimensions, all right, the modes will have the same structure as the original metric. So, in other words, since this metric is conformal to the Minkowski space time, the modes, Rindler modes, that is box phi equal to 0, solved in terms of the eta xi coordinates will again be plane waves with t replaced by eta and x replaced by xi. You can show that. Okay. And therefore, you can construct positive norm modes in the new coordinate system. And not surprisingly, they have the same structure as the Minkowski modes, where nu is my new frequency and L is my wave number and nu is mod L. Now, I can define a Rindler vacuum by demanding that BL of OR is 0 for all L. Now, what is the geometry of the Rindler coordinates? It is easy to understand. Notice x squared minus t squared is e power 2 g psi by g squared. This is clear, okay, which is a positive quantity. So, the Rindler coordinate trajectory corresponds to a hyperbola as described by the blue line. This corresponds to constant xi, and different xi will be described by different hyperbolae. And notice this accelerated observer has a past horizon, which is this guy, and which is a future horizon. And the constant eta surfaces are like these straight lines, and they will keep shifting like this. You know, it will go from minus infinity, eta equal to minus infinity will go like this, while eta equal to plus infinity will go like this. I will urge you to convince yourself of these arguments. And as I was mentioning, there is a past horizon here, which means, you know, waves, traveling waves can come and hit this observer, but this observer can signal, send signal across this future horizon, but he cannot receive from them. There is a horizon which has been created in the frame of the uniformly accelerating observer. And we will see this is closely related, the presence of the horizon is closely related to the fact that the uniformly accelerated observer sees the Minkowski vacuum as a thermal spectrum of particles. That will become clear in a slide, in the next slide. So, what do we need to do? You have the Minkowski modes, you have the Rindler modes, and we know how they are related. They are related to through the Bogoliubov transformations, and I just need to calculate the Bogoliubov coefficients, and they are relatively straightforward to calculate. You can calculate them, and they are given by this expression. Importantly, as I mentioned, the Bogoliubov coefficient beta proves to be non-zero, and where gamma is the gamma function. And you can ask this question: what is the number of Rindler particles, okay, in the Minkowski vacuum? In other words, what is the number of particles observed by the Rindler observer in the Minkowski vacuum? You find that it is non-zero, and in fact, it is a thermal spectrum with a temperature of T is G by 2 pi. I would urge you to calculate the numbers. In other words, what is the acceleration that is required to have a temperature which is possibly observable in the laboratory. I will let you, carry out that exercise. There is another way of understanding this, this thing that you have encountered. What we have encountered is inequivalent quantization. If you have two sets of modes describing this, a region of space time, the field in a region of space time, the quantization in these two frames need not be equivalent. That is what we have encountered. In other words, quantum field theory may not be invariant under a nonlinear coordinate transformation. That is what we have seen. There is another nice, very physical or phenomenological way of understanding what we have encountered here, and that involves the idea of a detector. This is very easy to understand, and it involves the Whiteman function, and it is a good application of the Whiteman function that we had derived earlier. So, what is a detector? When you mean a detector, what do you have in mind? Something, right? And you want to detect something associated with the quantum field. You have no control over the quantum field, right? The quantum field is a quantum field, it is present. And you take something which is supposed to interact with the field. If you have an atom consisting of an electron, it interacts with the electromagnetic field. You need some internal energy levels. And you ask, if I take the atom and start running, whether the electron can get excited. That is the kind of idea you have when I mean a detector. It has, this is referred to as a monopole detector. There is a m of tau. Tau is the proper time in the frame of the detector, and phi is your field. So, there is a m describes the internal structure of the detector, and for simplicity I am going to consider a detector with just two energy levels, which is a ground state and an excited state, and it is interacting with the field through this interaction Lagrangian. M is a property of the detector, phi is evidently a property of the field, and they interact through this interaction Lagrangian. And we are going to assume that the field is in the quantum state, in the vacuum state initially, and they start moving with the detector. And I would like to know at late times what is the probability for the detector to transit from the ground state to the excited state. And the script E that you have here is the difference in the energy levels between the ground and the excited states. And you can show up to the first order in perturbation theory, it will just involve the amplitude will involve m times phi, probability amplitude with a suitable expectation value, not an expectation value, transition element. Okay. You calculate the amplitude of the field to go from the Minkowski vacuum to some excited state. The detector has to go from the ground state to the excited state, but you are not interested in what excited state the field has gone to. So, you have to sum over all the excited states of the field, and you can calculate the corresponding probability, and what you will arrive as this G plus. I have used the notation G plus instead of D plus, because the field can be a massive field, for instance, and this G plus is the Whiteman function corresponding to the field. So, what do? You calculate your Whiteman function, you calculate it along the trajectory of the detector. You know what is the trajectory of the accelerated detector, for instance, and you have to carry out these integrals. This tells you the probability of transition of the detector. Now, if G plus is a function only of tau minus tau prime, right, you can have a situation where you calculate the Whiteman function along a given trajectory. It does not depend on tau itself or tau prime itself, but it depends only on tau minus tau prime. It is translational invariant in the frame of the detector, time translational invariant, in which case this G plus can be written as just tau minus tau prime. You go back to this integral, this argument contains only tau minus tau prime. So, the tau prime can be converted, integral can be converted over tau plus tau prime and tau minus tau prime, and there will be an infinity that will be left behind, because the rest of the integrals contain only tau minus tau prime. I can divide this p of E, divide by that infinity and define a rate, which is given by this. The rate of transition of this detector is just the Fourier transform of the Whiteman function. Okay. And now we can ask, what does the accelerated detector do? So, what do we need to do? We know the trajectory of the detector. I am just going to write it in a slightly different form, it is just a suitable choice. And we know the Whiteman function for a massless scalar field. In the Minkowski vacuum, it was 1 over sigma squared. So, I can substitute then, and I will have something which is a function of tau minus tau prime, and that happens to have the following form. So, I have a detector trajectory in 3 plus 1 dimensions, which is given by this expression. I just take this and substitute in my original Whiteman function, which was 1 over sigma squared. And along the accelerated trajectory, you find this. Okay. And what you need to do is that, remember, this is a function of delta tau, which is tau minus tau prime. I plug it in here and I calculate the integral. This is a nice exercise in contour integration. I will let you carry this out, and when you carry it out, you find that it is again a thermal spectrum with a temperature of T is equal to G 2 pi. This detector is often referred to as an Unruh-Dewitt detector. Those were the people who originally introduced. And this phenomena, it was originally introduced by Unruh and a little later by Dewitt. And this phenomena, for this reason, the fact that a uniformly accelerated observer sees the Minkowski vacuum as populated by a thermal spectrum of particles is known as the Unruh effect. And because there is a horizon and black holes have a horizon as well, black holes, you encounter thermal effects in black holes as well, which is referred to as Hawking radiation. So, with that I stop this lecture. We will return for the next lecture a little later. Thank you.